All right, class, we'll get started. So today we have more regression. So a lecture on some additional methods in regression, basically building on some of the other concepts that we've seen in regression so far. And then at the end of the class, so after we finish the lecture part, so probably about an hour from now, I'd like to go over quiz 4. So you should have gotten your grades back on quiz 4 posted to Canvas, right? You can see them on Canvas and on Gradescope. And again, the rubric is in the answer key that's on Gradescope. And as another reminder, again, quiz 5 is on Wednesday. Then we have a bit of a break before quiz 6, and then quiz 7 is during the final exam period. So the spacing gets a little bit more forgiving from here on. As a reminder, that quiz 5 is primarily covering material from 3 lectures, right? So not from today's, but from 12, 13, 14. So up through the material from the most recent lecture before today. And that material that was covered in that lecture is primarily covered in the homework that's due on Wednesday at midnight. So just a word of advice, maybe a word of caution. Make sure you look at that homework before the quiz. Okay, so you don't necessarily need to have functioning Python code, right, before you come for the quiz on Wednesday, but definitely make sure you're looking at that homework and using that homework as practice for confidence intervals, inferences concerning proportions before we get to the quiz on Wednesday. Yep. So 12, 13, 14, primarily 12, 13, 14. Right, but remember, for example, 14 builds quite a bit on material, on lecture, on things that we learned before that. Same thing for the other lectures. Yeah.
Lecture 12 is like a lot of those tiny.
Yeah, so I will. So lecture 12, and then also in nonlinear regression, we also had quite a bit of programming, right? So 12 and 13 were very programming heavy. So just like, remember, lecture 2 was also pretty programming heavy. And when we saw that on the quiz, there was, I gave you some Python code to basically understand or tell me about, and the output to that Python code to interpret, right? There was a box plot there. So I would say expect the same kind of, at least something like that on this next quiz. And as we move forward, we'll see a lot more of this kind of, things we do primarily in code. So expect questions like that problem on Python that we had previously, where I'll give you code and some output and ask you to then interpret that. Or maybe not even code, maybe just give you the output to describe what the test was and give you the output and ask you to interpret those results, right? So, for example, we have like ANOVA test results, right? We had box plots comparing multiple samples. We have results from our fitting algorithm in nonlinear regression. So I ask you to interpret things like that. That make sense? Yeah. So will there be a lot of hand calculation of ANOVA? There will be, certainly there were some formulas that we gave for how you can use some of the results from ANOVA to compute things like the F statistic. I would expect you to be able to do that, but I'll give you an equation sheet. My goal is to have the equation sheet tonight. I don't have the equation sheet yet, but to have the equation sheet to you tonight so you have at least all day tomorrow and Wednesday morning to look at it. Okay. Other questions? Okay. Great. So as I said, and for those of you who came in late, we'll review all the questions on quiz 4 at the end of the lecture. Okay, so we're going to talk about a little bit about some additional concepts in regression today, and that build on things that we've seen so far. So this is one of those lectures where we have a few different kinds of topics to get through that cover a couple of different kinds of scenarios. Yep, one more question. Today's lecture is not on the quiz on Wednesday. Yep. It'll be on the next one after that. Okay, so to start with, we'll look at some ways that we can apply linear regression to problems that seem like we might need nonlinear regression, but that we can actually simplify and then use those tools. Because we saw that for linear regression, we have, for example, an exact analytical solution for what the least squares, in some sense, least squares best fit to the line or to the data is. And so if we can transform our data into a form that is appropriately fit with a straight line, then we can benefit from those methods. So this is the idea of curvilinear regression, right? So in linear regression, again, we're fitting the model y is a0 plus a1x to our data. And so, on occasion, we'll end up with data that we can transform into a form that we can then fit with just a line. So an example would be exponential. So if we believe that our data is y is alpha times beta to the x, then if we take the logarithm of this, we end up with this expression, this equation 2. And now this has the form that we have some output, in this case log y instead of just y, is equal to some constant plus our variable x times some other constant. And so we can now take the same methods that we use for linear regression and apply to y, log of y as a function of x. Right, but all the same kinds of things that we did in lecture 4 would then, or linear regression would then apply. Another example is when we have data like this. So y is 1 over alpha plus beta x. We can transform this by taking the reciprocal of both sides. And we end up with 1 over y is now just a linear function of x. And so we can now apply linear regression to look at 1 over y as a function of x. Right, so remember when we did these are just like tricks we can do, right? Like math tricks we can do to avoid our nonlinear regression. Because in our nonlinear regression, we have all of these other issues that we had to worry about, like guessing, right? We had to put in a guess for what the values are, for what the fit coefficients actually are. But by using this method, we don't have to worry about that, right? If we can transform it to a linear equation, we don't have to worry about that. So another example is a power function, where again, we're going to take the logarithm, right? So this is y is alpha times x to the beta. So a little bit different from the exponential function up above. But again, we do the log transform. And now we see that we have log y is a function of log x. And so we'll just take that linear regression type analysis and apply it to log y as a function of log x. Okay, so that's the basic example. That's the basic concept. Yep. It doesn't matter actually. So in this case, this is log base 10. When I say log, like this is log base 10, but we could use whatever base we want and we would still get the same form. So this could be natural log. Yeah. So here's an example. So if we say that air exchange rate in a well-mixed room can be found by injecting a pulse of stable gas as a tracer and measuring how the concentration decays with time. And we have our data here showing as a function of time what our measurement was of concentration of the gas in ppm. Now, first we will plot this data. And if we look at a plot of this data for ppm or concentration of our tracer as a function of time, we see this kind of a curved line. So it looks like a linear best fit to this data would not give us an adequate description of what the trend is. So for example, if we did do that linear least squares fit and we looked at the residuals, we would see that there would be a pattern to those residuals indicating that there's some other curve which probably fits our data a little bit better. And so in this case, we can use what we know physically based on a material balance to predict that the concentration should be an exponentially decaying function of time. So if this is what we expect for the concentration as a function of time, what we can do, we can take the logarithm. In this case, we're doing natural log. instead of that log base 10, but either way works. So we do the natural log. And now we end up with a new form of the expression, looking at the natural log of the concentration as a function of time, with now two coefficients that we're going to find with our linear least squares fit. One of them will be the log, in this case, the natural log of the initial concentration, and the other of which is I, this basically this rate coefficient in the expression. So one thing to do if we have this data, so this is suggesting that log transforming the data will give us a straight line. So let's look at the log of the concentration that we measured as a function of time. So that is exactly what's done here. And in this case, it's done using the semi-log y function. So we could do this two different ways. One, we could just directly take the logarithm of the concentration data and plot that. Or we can also use a semi-log function to plot the data, which can be maybe a little bit quicker. We don't have to define a new variable. So we're using plot.semilog y. So we're telling it that semilog y tells it we're taking just the logarithm of that y variable. And yeah, there's a question. In this case, it's base 10. Yes. And we can tell that by looking at the labels here, that this is base 10. Yeah. I mean, if we were to do this sort of on our own, right, and instead of plotting ppm versus time, we directly just plot using the standard plot function. We plot the log of ppm versus time. Then we could make it the natural log or whatever else we wanted. Yeah. Okay, so in this case, when we make that plot, we see this data, and now this looks like a nice straight line. And so it looks like our exponential model will fit this data pretty well. And it looks like by plotting the log of y as a function of time, right, instead of just the concentration, we're plotting the log of concentration as a function of time, that doing so is going to give us something that is now amenable to our linear fit. All right, so there's our plot. So now we can just use the methods from lecture 4 for this, right? So we looked at a couple of different methods, for example, using OLS package, which we'll be using quite a bit later in this lecture. But we also had a set of equations, which we saw on a previous quiz as well, that allow us to just take the data and compute the intercept and slope by computing these intermediate variables SXY, SXX, SYY. And so this is really just copied out of your lecture 4 notes on least squares linear fitting. This is the same function that we defined in those notes that allows us to find the slope and margin of error and everything on the slope from essentially computing those SXY, SXX, and SYY. And when we run that, and again, this is actually pretty much exactly, this block of code is, again, pretty much exactly what we saw in lecture 4. The difference is that now our y is just the log of the ppm data instead of just the ppm data on its own. So when we do that and run it, we end up with a value for intercept and slope, right? But importantly, if we look at our R squared, we see a really high R squared value. So this tells us something about goodness of fit. We have an R squared value of 0.99. So if we remember, again, back from lecture 4 or from our previous lecture on regression, that R squared value tells us the proportion of the variance in the data that's explained by the model. So 0.99 means that, in this case, over 99% of the variance in the data is explained by the model. That's a very, very, very good fit. Right? For real data, that almost never happens. So that tells us we have a really good fit to this model. And then from that, we can also, again, using the methods from our linear regression, we can then put, for example, confidence intervals on our different variables. So in this case, I is just the slope. That was the air inflow rate. I was just the slope of our function, even our log transform function. And so we found that slope to be, the slope was minus 0.5, and our model defined that as minus I. So that means I is 0.5, and we put margin of error on that slope. We found that to be about 0.06, both with units of per hour. So this tells us something about what our predicted airflow air inflow rate would be. And when we plot the data, again, we see really, really nice fit. So this is now log of ppm versus time. And we see a really great fit. So the summary of this, after we got through that initial stuff, I think we moved a little bit quickly through this because this was material again from lecture 4. But in summary, we've seen that we can take, if we can transform our data to, or we can transform what we expect our model to be into something where we have a linear form, then we can use our linear fitting methods that we had from a previous lecture. Okay. Does that general concept make sense? Even if maybe there's some details you need practice on? Okay. Okay. So another thing that can be useful to look at is the residuals. In this case, we're looking at residuals as a function of what the predicted value was. And we see, there's some maybe trend in those residuals. We see it rising and falling, but the magnitude is not terribly large relative to what the data was. And so it looks like our model did an adequate fit. And again, that R squared of 0.99 indicates that we had a really outstanding fit between the model and our data. Okay, so moving on in regression, just another topic in regression is, let's say we have data that is clearly not linear, right? That clearly doesn't fit a linear model. And we can't take our data and transform it in some way that we get something resembling a linear model. Oftentimes, the first stop is to use a polynomial model to just get an approximate idea of what the data looks like. So if we really don't have a good understanding of what it is, then we'll use a polynomial regression. And this, the theoretical justification for this is, we're trying to, in a lot of this regression work, we're trying to figure out some function f that describes y as a function of x. And we know that we can use a Taylor series expansion to at least approximate that. And by Taylor series expansion, with the Taylor series expansion, if we make that expansion high order enough, right, then we can capture any function f, right? So the idea of polynomial regression is to say, well, okay, since I know I can do a Taylor series expansion, if I knew f, I could do a Taylor series expansion. So in this case, we don't know f. We're starting from the data, and we're seeing, what kind of polynomial would fit that data. And so we have then approximating what that Taylor series expansion would give us. So here's an example. Right, so if you don't really know what to do, but you know it's not linear, polynomial is a good place to start. So here we have some data looking at drying time as a function of some additive weight percent. Right, so we have 2 arrays of data defined. And so if we're going to go down this route, the first thing that we want to do is figure out what order of polynomial are we going to fit to. This is basically our decision that we have to make when we're doing polynomial fitting, is what order do we use? And so when we plot our data, we see this. So this is clearly not linear. Anyone, I guess, without reading ahead in the notes, anyone, like, what order polynomial would we use for this? Like first, second, third? I see a 2. Anybody else give me 2? About 3? I see a 4. So 2 is where we're going to go. Why 4? I guess I'm curious why 4. You miscounted. Okay. So that's okay. I don't mean to single you out, but so we, in general, so in this case, we see the data, dipping and then rising again, right? So we see some curvature in the data. We know that a parabola, which would be a second order polynomial, will capture that kind of curvature in the data. And the other maybe secret to polynomial fitting is you want to use the lowest order polynomial that captures the trend that you think is there in the data. Because if we were to take this data and we fit it with an even higher order polynomial, right? Like 1, 2, 3, 4, 5, 6, 7, 8, 9, an eighth order polynomial, we could get an exact fit to this data. But then it wouldn't really be, but that would be very much what we would call an overfit model, where we would be describing just exactly what happened according to, including all random variation within this data. And we'd be highly likely to get really strange results outside of this range. And so in general, when we're fitting with a polynomial, we want to use the lowest order polynomial that we can that captures the general trend that we think is there or think might be present in the data. So in this case, parabolic or second order polynomial fit would be appropriate because that's going to capture this general up and down trend that we see. So we'll use a parabola or second order polynomial fit. In this case, we're going to be using the NumPy function polyfit to do this. And then we'll plot the data and we'll plot the model. So we're using np.polyfit, where in this case, we're putting in the order of that polynomial fit. And when we do that, this is what we see, right? So we see, a relatively nice fit. We see a lot more variation between the fit and the model than we had in our previous example. This is honestly a lot better example of what you would see with real data, right? So it's not perfect, but it does capture that general trend that is present in the data without being such a high order polynomial that it's fluctuating up and down wildly to hit each and every single one of those points. So when we look at our results, we can then find for example, the array of coefficients, starting with the highest order term is the format of the output. So this would be our A2, our A1 in the middle, and our A0 on the right-hand side. And we can use then the covariance matrix, just as we did again in our linear regression lecture. We can use the covariance matrix to then find the confidence intervals on the parameters that we have from, on our coefficients that we found from the polynomial fit. And so in this case, we're finding standard error. We computed t-value for a 95% confidence interval for a two-sided 95% confidence interval. One thing to note here is that our degrees of freedom is n minus the number of parameters that we fit. So we fit 3 parameters. So our degrees of freedom is n minus 3. Remember, degrees of freedom when we were doing a linear fit was n minus 2. And that's because we had 2 parameters that we were fitting to. So something to be aware of when we're doing this kind of testing. And so then we can find our margin of error as the t-value that we found based on that number of degrees of freedom and our specified confidence level times the standard error. And so now we have confidence intervals on those parameters as well. Okay. So now we have a curve, right, defined by the parameters that were output from our polyfit. We have confidence intervals on those parameters. Right? We could, for example, use those parameters to find, for example, the optimum level. Like maybe I'm going to scroll back up to the data. So it might be that we've made these measurements because we're trying to find the optimum weight percent of the additive that gives us the lowest drying time, the lowest observed drying time. And so one approach would be just to find one approach that's a little bit too simplistic would be to just find the weight percent additive at which we observed the minimum drying time. But that doesn't account for the fact that we might have just happened to see an especially low drying time at this point because of noise in our measurement or noise in our system. So the better approach here is to do an appropriate fit to the data. In this case, we did a second order polynomial fit. And then that second order polynomial fit integrates in a least squares way, finds the best fit to the model, integrating all of the noise that we observed, all of the measurements that we observed, and actually predicts a bit different optimum for the weight percent of the additive. So it suggests that really we're going to look for an optimum somewhere around 5%. And this would probably merit more experimentation to really nail it down. But from this, I would expect that the optimal weight percent is somewhere around 5%. Right. So now that we have this model, we can then use it to do things like that, answer questions about where we think the optimum really is, or what is the expected drying time at a given weight percent. And we can put confidence intervals on that as well. Okay. So, and this whole idea of how we can use statistics to optimize and to optimize different process inputs or make predictions based on those process inputs when we have some complex system. This is called response surface analysis, and this is going to be the subject of something coming up in a few lectures. Okay, so we will come back to this concept, and we'll use some of these concepts from regression when we get there. Okay. So we can also use the OLS framework in order to perform polynomial regression. So remember, in this case, we need to use our pandas data frame, or have our data in a pandas data frame. We do need to put in another column in the data frame where we have to have a column in the data frame for every order of the polynomial that we would like to include in the model. So in this case, we have a second order model. And so in addition to having a column in the data frame that corresponds to x, we need a column in the data frame corresponding to x squared. In this case, we're just naming it xx and putting into that column the data.x times data.x, right? So we have that data squared. Our model, right? Remember when we're using the OLS framework, we tend to write out our model in text form, right? Based on the names of the columns in our data frame. And so our OLS model is seeking to fit y as a function of x plus this x squared. I know we're not telling it what we're calling the coefficients or anything, right? It's going to figure out what those coefficients are for us. So we're calling OLS.fit, and then we're looking at the model summary, the model outputs from that OLS method down below. And so this gives us a large amount of results, but some things to pay attention to and some things that we called out previously are, for example, our R squared. Right, so we see an R squared of 0.92, not nearly as high as the 0.99 that we had in that first example, but still definitely respectable, indicating that our model accounts for about 92% of the variation in the data. We can look at some other features here. Right, so if we look at these results, we'll see we ended up with the same as we had previously, but we can also see, like, for example, our t-values are really large or really far away from zero, indicating that we have really a high degree of confidence in those parameters as well. All right. Any questions on polynomial fitting? Okay. So we're rolling through a number of topics on regression today. Also, I want to make sure we get time to talk about quiz 4, because in the past when we have one of these lectures where we also talk about a quiz, it gets shoved into the last 15 minutes or so, and I'd like us to have a little bit more time if possible today. Okay, so multiple regression. So it is often the case, and we'll see in response surface analysis later, it will often be the case that we have some output that is not a function of just a single input, but perhaps a function of multiple inputs. And so in this case, what we're doing, if we're trying to find what that functional form is based on our data, then this would be called multiple regression, because now we have multiple inputs that we're trying to fit to our measured data. So in this case, we're looking at a linear model that relates our output y to our inputs xi. And what we're seeking to find based on our data are the values of all of those different coefficients, in this case, ai through am. And just to note, if we look at this expression, if this were in 1D and we just had y is a naught plus a1 xi1, right? If we just had, or it should just be, yeah, a1 times xi1, right? In this case, it's just a linear model, right? And that just describes a line. If we just had two terms here, plus our constant, then what we're describing is really just a plane, right? In three-dimensional space, we have some kind of plane, and so on. So we end up with, these are essentially like linear models describing higher order planes in multi-dimensional space. So this is a simple multiple regression model. So we'll look at this by way of an example, and we'll solve it using the OLS method for pandas data frames. So we'll look at an example involving the number of twists required to rupture a ductile metal that's loaded in tension. And we want to know how the number of twists depends on the weight percentages of two alloying elements present in the metal. So we have some data here that's looking at the number of twists, the percentage of our different materials that are in our alloy, right? So we have this multivariate kind of data set, and we're going to be using multiple regression to try to understand something about what we see within this data set. So the first thing to do, again, is to look at our data. And so in this case, because our data is higher order, right, meaning it's not just two-dimensional, right, we're only going to be looking at little slices of our data, right? So we're going to look at a slice of our data in one plane, and then slice of our data in another plane. So, for example, we'll look at the percent of B, sorry, the number of twists that occurred during this testing versus percent of that alloying element B. And we see something like this, right, where it looks like number of twists is in fact a function of the percentage of that alloying element B. And an important thing to take away from this plot is that it looks like there's an approximately linear relationship between those two things, right? There's definitely some spread there that's not captured, right? Some spread in the data that's not captured by just a straight line. So our R squared is not going to be terribly high if we were to just do the univariate linear regression between number of twists and percent B. But still, it looks like a linear multiple regression model might work. But to address that, we should probably look at, I don't have it plotted. Just double check I don't have it plotted. We should also look at the number of twists versus percentage element A, which, let's see if I can do this without making a mistake here. Right, and so when we do that, so now when we plot number of twists versus percentage element A, we also see a relationship that looks roughly linear. So this indicates that our linear multivariate model might work reasonably well for this data. I guess, yeah. Okay, so our scatter plot suggests that, these two things appear to have roughly linear effects. So we're going to see how combining the two in a linear way works. And so we'll use our OLS model, where now it's OLS for a number of twists as a function of percent A plus percent B. Note that this is very similar to the syntax that we used when we were doing the polynomial fitting, right? Second order polynomial fitting, right? So there we had our output Y as a function of our input X plus XX, which is where we put X squared, right? So here we have percent A plus percent B as the two parameters that we're going to be fitting against, right? So they're two different variables instead of just a square of one of the other input variables, but it's more or less the same syntax for input to the OLS model. So when we do that, we can look at our model summary. We're talking about using OLS model. This is the type of thing that I might give you on a quiz, right, and ask you to interpret some of the results that you see in this kind of an output. At least for the parameters that we've discussed in class and in the notes. And so from this, we can see, so if we look at just the coefficients, we start down here. We see that we have a coefficient for the intercept, a coefficient for percent A, and coefficient for percent B. So these parameters then define what our fit is, or what our least squares fit is. So from that, we put that back into the formula that we were regressing against, right? So we had two inputs, x1 and x2, right? This was percent A and percent B. So our full model was some constant plus some coefficient that we were trying to find times percent A plus another coefficient we were trying to find times percent B. And from that table, we can read out that our intercept was 46.3. Our coefficient times percent A was 7.8, and our coefficient times percent B was minus 1.6 or 1.7. We can then also from this data see standard errors of the regression coefficients. So that's given here, as well as we have confidence intervals provided on those coefficients. We have an R-squared value indicating that the model explains about 92% of the variance in the data. So if we look up here, there's our R-squared value indicating that, consistent with what we saw in the plots, it looked like the data was roughly linear in both variables. And so we have a really nice high R-squared, again, indicating that that linear model was appropriate. The p-values, so in this case, we can interpret these p-values that are given here and the large t-values as in they're far away from zero, or absolute value of these numbers is large, right? Indicating that these t-values are far away from zero, or very low p-values, right? So these two things correspond to one another. That indicates that that all terms in this model are needed. One way to interpret it is whether or not percent B is needed to help explain the variation that was observed in in this case, the number of twists before failure. And the fact that we have really low p-values indicates that, yes, we do need those terms. In this case, we need all terms in the model in order to explain the variation that we saw in the data. And another way to think about this result and to interpret the data that we have out of that chart is, so that's our model, right? Our multivariable model to understand what this data is, to understand number of twists as a function of percent A and percent B. So we can, for example, interpret that A1 parameter as telling us something like the average increase in number of twists for each increase in A, while we hold B constant. So it tells us, those parameters now tell us how much the output changes as a function of our two inputs. If that makes sense. We could also then use this to predict for a given percent A and percent B, what is our best prediction of the number of twists that we would see in this material before failure. Okay. All right. We have one more example on multiple regression. We're turning our attention back to quiz 4. Any questions on this so far? So to this point, this multiple regression and the polynomial regression we've looked at them more or less as other applications of the least squares curve fitting methods like OLS that we've seen previously. All right, so the second example is based on data from Micron. And this is about making some kind of a silicon chip. And in this case, we're looking at changes in 6 individual processes. And we want to know, does this affect quality or not in our final output? And so we have some measure. So if we look at the data from Micron when they were called IM Flash, we have some measure of quality as a result of the processes. And all we have on the processes are, again, this categorical data of saying whether we use the old process or the new process. So old is 0, new is 1. And let's say you as the engineer at Micron are now tasked with identifying like what to do, right? Which processes should you replace? Which processes should you update? Which processes should you keep with the old one because the old one was better, right? So this is a case where, again, we have now not just 2 inputs like we had in the previous example, but we now have 6 inputs. And we have our output. And so we can use multivariable regression in order to try to get a handle on what's going on in this data. Yeah, we want to know which changes affect quality and which ones are beneficial. And we're doing so with categorical data, right? So we don't actually have some kind of input measurement for each of these. We're just trying to see if for a 0 or a 1, right, old or new, which ones are actually going to work. So again, we're going to use OLS on this data, which is loaded into a pandas data frame. And now our model is quality as a function of all of our different process variables, which again are coded as 0 or 1 for old versus new. And when we look at this, this is our output of the regression. So can anyone tell me something that maybe is very different about this result from this example from what we had previously? R squared, yeah. R squared is super low, right? So our model only accounts for about 9% of the variance. So our model does a pretty poor job of describing what's going on here. So to really understand this, we would have to go actually quite a bit further. But we can get some sense, we can get some ideas of what's going on in this data, even though our R squared is so low. So accuracy of the prediction is really poor. As indicated by that low R squared, it's really poor. But nonetheless, we can look at the coefficients. We can still say something, even if we can't say it with high confidence. We can still start to say something about what this data is showing us. So if we look at our coefficients here, we see that for PA, PC, and PE, we have negative coefficients, which, and again, you have to be careful with the language here, it suggests that these new processes may hurt quality, right? So remember, the process variable equal to 0 means we're using the old process, 1 equals we're using the new process. So if we have a negative coefficient in our linear model to these process variables, then that means that increasing that, let's say that PA parameter, decreased the quality, meaning that going to the new process decreased the quality. And the same for C and E. However, the low R squared, the high P values on all the coefficients give us little confidence in most of these results, right? So aside from the intercept, we see that we have relatively high p-values, meaning we cannot say with much significance that these are having that kind of an impact. But if we were to look at this, we would see that one standout is that process F. This still doesn't meet that 0.05 level of significance that we would ordinarily apply, but nonetheless, it is by far the lowest p-value among included in what we've observed. And so, if you were the engineer looking at this data and trying to make something of it, right, at least as a first pass, from this, you might conclude that process F has the greatest likelihood of improving the quality of the wafers. And this might be the thing that merits the most investigation for ongoing work, okay? For example, we can still see that our confidence interval on that process F coefficient includes 0. And so we really don't have very high confidence that that this variable does have an impact, but it'd be the next thing that we'd probably look at if given this data. All right, and that wraps up our lecture 15 on additional topics in regression. Are there any questions on this before we move on? Okay. Again, this is not on the quiz on Wednesday, but it'll be on the next one after that, okay? And we will use these concepts in our response surface fitting lectures to come. All right, so if there are no further questions on this, then I'll give anyone who doesn't want to be here for discussion of the quiz a chance to clear the room. And then after a couple of minutes, we'll pop open quiz 4 and talk through the answers to quiz 4. So thank you all.